Alright, so I got another physics demonstration here. Here I have a couple objects. First I have just your basic screw and some neodymium magnets here. So some pretty strong magnets, and as you can see the screw is attracted to the magnets. And I also have just your basic AA battery for a voltage source and a trimmed down copper wire here so that we can complete a circuit. So before we actually start here, if you didn't know, this actually does work. Putting a wire, just as simple as that, it conducts electricity, and you can tell because the copper wire actually heats up. So I'm going to let that cool for a second. But what I'm going to do here is I'm going to attach the magnet with the screw, and I'm actually going to attach it to the positive terminal of the battery. You can attach it to the negative end, which is how this is conventionally done. But it seems to work better. It seems to hold more steady when I do it this way. So what I'm going to do here is I'm going to try to complete the circuit again, except this time I'm going to conduct the electricity through the magnets in the screw. And since these are neodymium magnets, they will conduct electricity, so I actually have a complete circuit here. But the key is to look at what happens to the magnets here as electricity passes through this circuit. So you see that? Let me get closer just so I can make sure we can see on video. What happens here is the magnets start spinning, and you can get them up to pretty high speeds. So why is this the case? Why does the magnet turn and we can actually get it to rotate at very high speeds when the current carrying wire is brought close to the magnet? Well, what happens here, and we can look at this as simply as the right-hand rule, and we know that the magnetic force for a current carrying wire that's in a magnetic field, we can use the right-hand rule. So looking here, we have the current going this way, and due to the configuration of the magnets, we have the magnetic field going up. So we know that the force must be going into the phone, what I'm recording with, so it'd be going this way. So that means that the magnet would then turn this way. Now let's see if that happens. So as you see, the right-hand rule plays true. So it's turning in a counterclockwise direction. So the force is pointing inwards. Without going into too much more detail to make this video too long, this can also be explained as what is known as a homopolar motor. So essentially what happens here is that since we have current going perpendicular to the magnetic field of these wires here, it actually exerts what is known as Lorentz force on the current carrying wire. That obviously, Lorentz force involves both electric field and magnetic field, which would make sense because we have a current carrying wire and a magnetic field because of our magnets here. But we could go on for a while about that, so I'm going to end it here. Thank you for watching.